Hello everyone. I am Sanayat Fanta from IIT Kanpur. Uh, Originally, I came from Ethiopia, Defense University College of Engineering, and I am working as a research scholar in Indian Institute of Technology Kanpur these days. So today, I want to give a brief stepwise uh, abacus modeling procedure for impact analysis. Actually, most structures are subjected to impact from foreign objects. So, how that can be modeled using the different finite element simulation tools. That will be the intention. So the objective is to analyze the damage and the deformation that occur from the impact from some rigid impactor to the deformable structures like a plate of aluminum uh, that constructs some structures. So I'm going to provide you a step-by-step procedure, as well as practically I will use the Abacus software from my PC only, and we'll go parallel together with the slides as well as the model. Sorry. So let me share the slide with you. Sorry for the interruption. Some choking is there. Okay. So let me share the slides. Uh, okay. So the basic intention of this presentation is to model the impact analysis. That impact and the crash analysis are the most usual happenings in structures. So, whenever a foreign object impacts the structure, for example, in the case of aircraft, the service provider cars like the air supply and other uh, are come in contact with the structure itself and make an scratch or impact or crash on the structure. So how we can model those things, and whenever the aircraft is in flight, maybe it subject with the bird impact, or whenever the aircraft is going on the runways, the stones which peeled out from the road will impact the structure of the lower part of the wing, as well as also the cars which are uh, impact to each other. That actually crash analysis is the part of this thing. So let me see how we can. So for this purpose, uh, the model contains a rigid impactor. The impactor is made from rigid material that we consider impactor as stronger than the structure, so that impactor is modeled as a rigid impactor, and the model is considered as softer than or less stronger than the impactor, so that it is considered as a deformable aluminum plate, so that both are modeled using Abacus CEE. So this tutorial covers basic examples of spherical shaped object being fired on the aluminum plate. That The spherical shaped object is considered as the projectile, that it can be bullet, it can be even some object which is impacting the structure. And it needs the knowledge of abacus use. So abacus knowledge is required this time, and it also requires abacus software. That abacus CAE software must be installed to your system, and sometimes it needs some Fortran, Intel Fortran compilers also. Uh, for the system which needs user material subroutine, Intel Fortran compiler also required, so that this tutorial will take you all the steps required to create model and run the basic abacus simulation using abacus CAE, and finally to visualize the result. Okay, so that is the intention of this model. So what are the basic steps required to model the abacus, this impact model in the abacus? So the first step is opening the abacus CAE. That is the first step. So let me do that with my PC system. So let me open abacus CAE from my PC. So this is abacus CAE. I'm directly opening from my computer. So let's, until it open, let's talk on our slide. So from the start session menu, select create model database with standard explicit model. Set work directory for proper data saving and for particular work. To run the simulation in CAE, you can either work with various modules or the various work trees. We have alternative options. There is a work tree or workflow tree, or there is a, CAE, no, modules. Sorry. So the part module is used to define geometry. So different modules are there in the module, part module, uh, then property module, assembly module, step module, interaction module. Again, after interaction, boundary module, okay, mesh module, and finally, visualization module is also there, and the job submission module also there. These all modules are there in the system, so we can see each of them. Okay, so let's open and let's see this thing. So whenever we are opening abacus, we can see this thing. What it means? Look here, with standard explicit method, with CFD method, with electromagnetic model. So in our case, we are using standard explicit model. So we click on this. Then this is our abacus working environment. On this abacus working environment, what I have said is this thing: part module, property, assembly, step, interaction, load, mesh, optimization, job, visualization, sketch. These are there. So, and we have a workflow table is here, and there is modules are here. This can give different. This can give the same as what we have here. Someone can use this flow workflow tree. Someone can use these modules. Okay, so let me use the modules. So for anyone who want to work on work tree, can work. Both are the same. There is no difference on them. Okay, when I come to the Abacus modules, for different module, we can see different working environment. For example, in the case of part module, we can see the main menus of work module, the part module. These are main menus. If I change part module to property module, this all will immediately change. Let me switch to the property module. You see, these things are all changed. Previously in the part module, what are there? Okay, here file, model, view, port, view, part, shape, future, tools, plugin, help only. Then when I change it from part module to property module, some are common, okay, but material, section, profile, composite, assign, special, future, these are different. And also, if I change it to assembly, we can see instance, constraint, future. And when I change it to step, then step, output, others, this comes. And each of these things has a different function. Okay, so in each module we can see different main menus. Anyways, let's come to the first module, that is part module. So according to our lecture here, so the part module is the one which we are going to use. Okay, so uh, then I already discussed the working environment of Abacus. Okay, so the first step in our this analysis is creating parts. So we have two parts. The first is plate, and the second is the impactor. So we have to create plate and impactor separately first on Abacus. Let me go to the Abacus system and create these two parts. So I am in part module now. Create part. This means create part. Give the name plate. 3D deformable solid extrusion, and I'm going to use metric system. So approximate size, let it be 0.2. Continue. So this is a plate. I'm using this. These are the geometric entities which we use for creation of the geometry, that are point, line, circle, rectangle, ellipse, and other curved profiles. It can be arc, or it can be spline curves. So others are also there. So I selected the rectangle. So I can simply draw a rectangle of some dimension, and I can provide dimension of the rectangle. So in our exercise, the plate size is considered as 150 in the X, 100 in the Y, and the thickness is given to 2 millimeter. So that is aluminum plate of 2 millimeter dimension is considered. Okay, so I drawn a rectangle, then I will give dimension to the rectangle. Okay, here add dimension option is there. So add dimension, click on this and gives a dimension 0.15, that is 150 millimeter. Okay, again click on this 0.1, that means 100 millimeter the Y dimension or B dimension. Sorry that I made mistake, I give one, so I can delete this and I can give dimension again to this object 0.1. Yeah, now so the dimensions are given. Okay, Now, I want to place this rectangle at the middle. So for that, I need center point of rectangle. That helps us in assembling, proper assembling, okay, without any doubt. So let me move this rectangle to the center of the grid. Okay, this point to the center of the grid means this point. Okay, yeah, it is here. This is 150 by 100 millimeter rectangular plate size, and I will give thickness of the rectangle through uh, extrusion. Okay, depth extrusion, that is 0.002 meter. That means 2 millimeter. So this is our first part. That is the plate. We created plate, and the second part is impactor. Okay, let's see. Let me give the name impactor. So impactor is created with discrete rigid impactor because we consider a stronger impactor than the structure itself. So discrete rigid from shell revolution. So to get proper shape, let me use these options. Okay, then let me draw a circle. So our impactor is considered diameter equal to 12 millimeter. That means radius is equal to 6 millimeter. So let me give dimension of 6 e minus 3. Yeah, so this is the impactor radius. And let me construct some other features of impactor. And let's trim the unnecessary portion of this geometry or unrequired. Now this is the required portion of the our shape. Now I'm going to revolve it for 360 degree. Okay, so edit revolution on that parameter. By default 90 angle 90 given, that is for quarter model, but for full model 360 is required. So this is the impactor. So this rigid impactor is needs some reference point. That reference point helps us to define the load, define the boundary condition, define important parameters through that point. Okay. Most of the time, that point is expected as the point where mass concentrated on it. But let's give a reference point for our simplicity at one of the nodes at this point. Yeah. Yeah. Immediately you can see some reef is come. That reef RP represents the reference point. So that for most rigid, discrete rigid element, this thing is required. Now we have done all important procedures of the part module. Now part module is done. Okay. In part module, we are expected to draw the plate. Yeah, plate is already done, 100 by 100 with thickness 2 millimeter done. A rigid impactor of 6 millimeter diameter is created. Okay, reference point also created. So this is the procedure. And the next second step is defining the material property. Now I'm going to define the material property. How we can define um, aluminum material that is considered isotropic material that can be defined in terms of the Young's modulus of material, Poisson ratio of material, and the analysis is dynamic analysis, that dynamic explicit analysis. For that, we need density. So density is also required. So we introduce these material properties and assign a section to the materials. And in the case of impactor, the only material property is the mass. The remaining properties are not required because we selected discrete rigid material. So let me define material for the plate using abacus. So all these steps will be performed in the practically as let me switch off my module to property. Then on property, create material. Then let me give material name aluminum and the density, general density. Here it is 7,500. That means 7,500 kilogram per meter cube density. And the elastic property of aluminum is uh, mechanical elasticity, elastic. And then, sorry, I'm facing some choking, so please just ignore this. So here, the type elastic type isotropic. But in other case, in most laminated plate case, we use engineering constant or laminar property or orthotropic property or anisotropic property. And in the case of interface layer, we use traction property or coupled or either uncoupled traction property. But now isotropic property, the default one is sufficient for us. So let me give the dimension 72 gigapascal, that is E9, and Poisson ratio 0.3. Okay, 0.3 is the aluminum material property. No, here we are not going to see some other, the plasticity behavior and or other thing. We are simply looking the elasticity behavior so that the plasticity behavior will be another age of the analysis. So, so these properties are sufficient for the time being. Okay, so, okay. Now, let's assign create section. Create section, solid homogeneous section. Continue. Okay. And now the next step is assign section. So for assigning section, I have to select switch to plate, not the impactor. Assign section, select plate. Okay. Okay. Yeah, immediately once I assign a section and material property to the plate will change from white color to green color. This is the plate. Now, the material property, the only material property that I can provide, the property that I can give for impactor is the mass. How can I give mass? Um, um, Special inertia create. Okay, then point mass, continue, then select the uh, reference point, then give the isotropic mass, that point mass. Let we consider 3.132 kg. Okay, and the rotary inertia part, that I11, I22, I33 remain blank, left blank. Okay, so now okay. So immediately we can see some green dot here, which implies mass is assigned to that reference point. Okay, so it is better to give some set for the reference point because we are going to extract some important outputs through that point. So for that, let me use tools, set, create. Then let me call the set as ref. reference point. Okay, continue through the reference point. Okay, that is selected. Now the property module, the expected properties are already defined through the property module. Okay, so this is the slide which shows how we can introduce the material property, the assign the material property, and section properties. Especially that assigning section is very important for beams and that links like 1D trace elements, especially 1D bar elements need their dimensions through the section property. Okay, the next, these are what we have done. These are all done. This mass, impactor mass is already assigned. So this procedure helps you easily to assign the impactor to the mass to the impactor. Okay, the third one is create an assembly. Create an assembly. So these two parts must be assembled together. How we can assemble that impactor and the plate will be assembled. His plate, his impactor. Then finally, when we assemble, we can get this type. How we can do this? Let me go to. So let me switch to assembly. Yeah, here create an instance. Okay, click on plate. Actually, let's switch out of set, switch on, plate, apply, impactor. Okay, both of them come together here. And let me move this impactor to the center of impact center that I can translate it. Let me use this point as starting point and ending point 0 comma 0 because our ending point 0 comma 0, so it is directly to the 0 position. Now I have to rotate this impactor to proper location. That is, I have to rotate it to x-axis, about x-axis. So using these 2 points, then minus 90. Yeah, now it is in its proper location. So this is the assembly. So if we are doing laminated plates, the procedure of assembly is also the same. There is no difference. That is only we add more plates on it. For example, let me do one more plate on it. Let me stack one more plate on it. Yeah. Okay. But it is not our own intention. I will remove this later. I will delete it. So how we can stack it? I'm just moving it. Look, this is a laminated structure now. This is the laminated structure consisting two plates or two plates. Then all the procedure the same, except we add more interaction for the plate-plate contact, and we add uh, we have to give the orientation of the plates. Rather than that, everything is the same. So let me remove the current play because that is not our interest. Yeah. Let me go to uh, part, not part, with assembly here. In assembly, we have three things. Second play is not required, so I'm going to delete it. Delete. So this is our aluminum impactor with aluminum plate with impactor. Okay. Then the next is step model. We will go all steps in step by step. So step model is the uh, fourth step for our work. So creating an assembly of the part is done. Okay. Then the next is defining step. Now we define the step which specifies the time interval of simulation as well as various options defining the finite element algorithms. The state model is also used to define variables that will be saved to the output data during analysis. That history output as well as um, uh, mm, history output will be defined in this step. Uh, Other outputs also. So how we can define those things? Let me go to the so in the step, this is create step. Okay, we can give this name of step as impact. Okay, then the procedure type is general. This linear perturbation is there, but general procedure. Here by default it is static general analysis, but we are using for impact analysis either we use implicit, dynamic implicit or dynamic explicit. So this implicit and explicit is a matter of the algorithm which we are using. So let me select dynamic explicit. So continue. Then let me provide time interval of 0.006, that's 6 microsecond. And the remaining settings remain same. Same, then here uh, we have defined some reference point. Through that reference point, I need some force time curve, displacement time curve. So I have to, these are outputs actually. One is the field output, another is the history output. So by default, there is this thing in the field output, the stress, strain, displacement, reaction forces, contact. By default, these things are there. So it is as it. I'm not going to touch it. Here also in the history output, by default, we can see uh, the energy is as it. Okay. Uh, I'll add some more here that for our impact step, um, through the set which I provided the reference set. Through a reference set, I want some plot of displacement U3. I need some V3 velocity on that. Okay, 3 implies Z direction and reference RF3. Reference, not reference, but reaction on the Z direction. And I want to switch on the status here. Status. Okay. Sorry. Okay, I can give it through this U3. Okay, here B3. If needed, A3. Okay, let it be. So these things are there. And okay. Now I have to define some interaction property. Sorry, I'll start it later. Just Okay. Now, uh, we have some other option left. We'll come back after making interaction, because after interaction, the interaction between the plate surface and the tool surface or the impactor surface, on that there must be some outputs which we can extract from that. That will become later after and try defining interaction. Okay. Now, so these things all defined. Okay. This non-linear geometry box also checked there. This thing, non-linear geometry, this is checked there. Okay, it is on status. And this step model allows us to select variables to write that already I defined these things. And we first need to define a node. That node is a reference node. I already created that node and call it as ref. Okay, then select that ref. I did it. So to create output request, so history output request, um, through a reference point that I already checked it. So now the fifth step is the contact definition. Our fifth step is the contact definition. The contact between, if it is a stack of laminates, the contact between plate and one plate to another is also defined, either tied to each other or contacted with general contact algorithm. But in this case, the plate is only single plate and the impactor is making contact at a point or on a surface, so that that contact surface must be defined. How we can define that contact? Let's go practically how we can define. Okay, these all steps are, let me go to the practical one. Let me read. Name the property general contact and select the contact option, then press continue. Select the mechanical normal behavior, accept the default, tangential behavior, check the frictionless. That is also default. Frictionless is the default there. Then press OK. Next, specify at this point. Sometimes we can define, not sometimes, most of the time in general contact domain, we define the friction of some amount. From 0.2 to some 0.5, we can define the friction constant, that using penalty friction. But by default, frictionless is there. So in this case, let me exercise with frictionless. And then two surface with contact, we select the surface that the name of the two contacts as plate impactor interaction. So let me go to Abacus. So now the step will be switched to interaction. Okay, so in interaction, uh, create interaction, general contact explicit. Okay, continue, go to here, contact, let me call it as plate impactor interaction. Plate impactor interaction, continue. Here, mechanical property, tangential. Here it is size frictionless. Okay, sometimes we use penalty friction here, penalty friction. Then if I select penalty friction, I have to provide some friction coefficient of some value here. But let me use the frictionless contact with finite sliding of, so surface to surface finite sliding, so frictionless. And mechanical normal behavior. This is the default setting, hard contact, and constraint enforcement method, the default one, and allow separation after contact. Then okay. So okay, then what we can do? uh, Contact. Mm, we can go here. Actually, for this, we have to define two surface. Uh, okay, surface to surface contact, surface of the plate. Again, second surface is surface of the impactor. Uh, then, so the brown color one is considered the normal outward. So here, finite sliding is selected. Okay, uh, that kinematic contact method finite sliding. Okay, so first surface is surface one, surface two. Okay, we can switch it. Yeah. Okay, so we can see this. And then the next step is constraining the impactor. How we can constrain the impactor? Uh, Create constraints, rigid body, continue, body element, okay, edit selection, select the impactor. Not all the model, but only impactor. Select only the impactor, and then reference point will be selected. Then okay. So this interaction is already done. Okay. Then after interaction, we go back to step. Why? We have to define the uh, uh, some parameter here. Okay. Okay. History output. Here interaction. Either interaction or general contact surface will be selected. So let me select interaction. So on that interaction, I want to define uh, total force due to contact pressure along three direction. Uh, Total force due to friction stress. Actually, no friction, not required this. So because if there is no friction, these two things are not required, friction and so that is sufficient. CFN is sufficient. Okay, so that is defined in between this. So what is the next step after interaction? Contact definition. Okay, we created contacts and surface to surface contact, and then frictionless finite sliding contact is defined, and then CFN is defined. So let me, I didn't define that area, total area under contact. So let me go to define that area under contact. So um, here, let me edit it, edit. So this area under contact is not defined. Okay, done. So what is the next step? This, okay, creating constraint to the impactor is already done. The sixth step is the boundary and initial conditions that we have to assign the boundary conditions of the plate and the boundary condition of the impactor. Uh, that means the plate should not move in the z direction downward. So we have to support the plate from the bottom. And the impactor should not move in the x and the y direction. It only give translational motion in the z direction only. No rotational, only z translational motion allow for the impactor. So that this must be defined. How we can do that? Let me go to the model. So load here, create boundary. Yeah, name of boundary, let it be simply supported boundary condition. Okay. Uh, Capital simply supported boundary condition SSBC, symmetric, anti-symmetry, and inconstant. So mechanical for step, we can make it initial. Okay, continue. So let me select the four edges of the rectangle. While I am selecting the edge, I have to handle shift with the mouse. Unless the one which I selected will cancel after I go to another selection. Okay. So these are the boundaries which supports the plate from the bottom. Okay. For that, let me give pinned condition that restricts the motion in U1, U2, and U3. That transmotional motions are constrained, but rotational motions are not. But if I give in caster, that is completely fixed boundary condition and all degree of freedom will be constrained. So let it be pinned. Yeah, this is the plate is pinned now. And the next is the impactor must be given only Z translational motion only. For that, uh, create boundary. So uh, Z movement, the name, displacement, mechanical displacement for the initial, continue through the reference point. Okay, through the reference point, I'll check U1, U2, U3 will be free, that it allowed to move in U3. UR1, rotational motion constraint in 3 direction. So except U3, they all are checked. And then okay. So here it is constrained. So only move in the Z direction only. Yeah. So what is left now? The remaining thing is giving impact velocity to the impactor or the motion of velocity of the impactor. How can I? So we have no experimental amplitude data that helps the pattern of the motion or the displacement of the impactor, so that we cannot easily define the velocity of impactor on uh, this great boundary condition situation. So I have to give it using free-defined field. Here, create free-defined field is there. Okay, on free-defined field, mechanical velocity is there. Okay, velocity. Then I select the point where velocity will be given. That's through the reference point. Okay. Now through the reference point. Okay. So let 2.5 meter per second. Okay, that is this direction. So I will give only positive z direction, and v1 and the v1 and the v2 remain blank. Okay. Then Okay, so we can see, look, this is the velocity given, the impact velocity. Yeah, once this is given, the next step is, according to our procedural slide, once we satisfy the boundary conditions of all the parameters, what is the next step? Let's see. Yeah, boundaries are provided. These are all what I have discussed. Yeah, okay. Now the finite element mesh is the next step. So this mesh means uh, in finite element course, we know that we discretize a given volume or a given geometry into any number of elements for simplification of the analysis. And we will see um, that individual elements property in order to evaluate the whole system. So we have to mesh the system. That means we have to discretize it and provide proper material mesh control systems. So in this case, uh, to specify the element type that will be used in the analysis, select mesh element type, then click on the plate and select that. In the element type menu, select the explicit element library because what we are doing is explicit. We have two options, standard and explicit. So we select explicit and then allow the material removal, that selecting the material deletions, and selecting also the control of spurious deformation of material due to hourglassing effect. That should be also selected. So let me do it practically. This the meshing procedures all written here. The global seed of the mesh is for the plate is 1.5. Okay, so let me go to the model. Okay, mesh. So this is the mesh model. The first thing is I am going to mesh it part by part. Okay, this impactor with seed of let it be 1 millimeter. Apply okay, then mesh only. So element selection is not required for the impactor because it is a discrete rigid element. But let me come to the plate. So for plate, let's seed the part. As I said, it is 1.5 millimeter. Apply. Okay, this is the seeds, the global seed. Okay, that is sufficient, I think. And then we have to assign mesh control. So in mesh control, element shape hexa dominated element shape is selected, and the structure type. One can use sweep, one can use bottom up. So each of these algorithms are based on the interest, and one can refer the Abacus user manual to know what each of them, because that is a vast topic that I cannot cover here. So please refer the Abacus user manual on internet, which is available there. One can use hexa dominated, one can use hexa, one can use theta, wedge. Here the technique, structure technique, free mesh technique, bottom up technique, and others. Okay, so for now I am using hexa. Structured techniques are applied, and then uh, the element assigning the element. So I'm going to assign element for this plate, and at the same time the explicit analysis. Our analysis is dynamic analysis, so that we cannot use standard. In standard, uh, already we selected in step, we selected dynamic explicit, so explicit linear analysis, 3D family of the material. And then here, hourglass control, enhanced hourglass control selected. And another important is element deletion. This element deletion allows us to delete the damaged material from the system and retain undamaged. So we are allowing the system to delete damaged material. So once then what we selected is C3D8R element. That is called an 8-node linear brick element with reduced integration and hourglass control. Okay, so then okay. Then we will mesh it. Mesh the part. Yes. So the part is now meshed. And the mesh assembly seems like this. This is the mesh assembly. Very nice. Once the part is meshed with proper mesh type, okay, then it should be go for further analysis or further step. That is, we have to create a job. Okay, so we have to run the job. To run the job, we have to create the job. Okay, mesh is already done. So create a job rather than run the job, but create a job. Let me explain on that. So finally, you will need to set up and submit an analysis. Select the job module to do this. Select job create, name the job. For example, I name the job as impact simulation. Somebody may give his own name, that depends. So you can accept the default for all other options, but um, in the case of material subroutine, the use of material subroutine, or while we are using material that created by Fortran language, then we will switch off to some other direction than the default setting. Okay, and then run the analysis, then select job, submit. These steps, let me go to one by one. Okay, this is now the next step is job. Then the module is job module. Okay, on the job module, create job is there. So the job name, let me call it as impact simulation. This is the job name. Continue. Now, at this time, I'm going to use all the default things and say okay. But if I am using the material subroutine, then I'll go to general and use subroutine files. And clicking on that, I'll run the Fortran run material subroutine. So that is not here now. So now I'm just saying okay with the default setting. Okay. Okay. So now the impact simulation job is ready for running or submitting. So I'm going to submit the job. Okay. If there is any mistake in the job automatically abort, or it will give a warning message. So let's see. Submitted now. It says analysis is submitted. Okay. Yeah. You can view the progress of analysis along with view messages by the select. So if Abacus detects any problem in defining the analysis, it will show errors and warnings. So you can view the progress, even each progress of the analysis we can see at this time. And you will see one warning, some kind of warnings are there, which is harmless. And some warnings are that can abort the running of the system. So what are the warnings in our analysis? Let's see. Yeah, it is now running, it says. So in monitor, clicking on monitor, we can see many things. So this is the monitor screen. Okay, and this we can see many things. Impact simulation, it is started running. Okay, time step increment, total time, CPU time, step time, stable time increment, kinetic energy, total energy. These all are here. Now there is no error in this case. Some warnings are there. Yes, obviously. The one warning is there are one warning message in the data dot file. Please check. So that this is expectable and harmless error. That's why it is the job is not terminated or aborted. So that it's okay. Here we can see the output. By default, there are 20 step of output frames of output defined in the step, so that from that it ran now for dot file, message file, status file. These all are here. If I don't want to continue running, I'll say kill here. Kill is there. Okay, so these all options are there. Okay, let me say something on run files. Okay, file types in Abacus run. In Abacus, creates large number of files during an analysis. What are those large number of files? We'll go back to the directory which we saved all our file, and we can see them. It is not only the CAE file, but a number of files are now generated there. Just when I run it, many files generated. So the following files can be viewed using the text editor. Some of the files we can view them in using text editor. That the text editor means like, let me show you. With this, people can check or open some files that notepad plus plus or simple text editors can help us to open some of the files. Okay, so this node plus plus or file is important. Okay, so what are the files generated during the simulation? As soon as I run the impact simulation job, the impact simulation.imp, this imp file generate, log file generate, stat file generate, message file, file, msg, sta, log, imp. So this imp file is an ASCII file that defines finite element simulation. So this is how the Abacus working environment or Abacus CAE interacts with the user graphic system or GU, graphic user interface of the system, which communicates with Abacus finite element platforms. So we often edit the file and run Abacus with it directly when we use Abacus with user element or user material subroutine. So this user element or user material subroutines are separate files which are created in Fortran language and run to the Abacus system using the this uh, job in the job module. So Log file summarizes the outcome of each phase of the analysis. Start file is updating during analysis to show its progress, and msg contains error message, and .dat file contains both error message and output of analysis. So it is sometimes the only way to easily view result of analysis that has a user element shows. So the last step is extracting a result. Once our analysis is finished or successfully finished, completed, then we have to see the outputs. That is the post-processing part. So in any finite element analysis, uh, post-processing is the result extraction step. Okay, so that post-processing, pre-processing, modeling, post-processing are the three steps. So that extracting the result is the post-processing. How we can do that? Let's see whether, yeah. Now our file is already completed. Running is completed. So that what can I do? I click on results. That immediately took me to visualization, or I can click on visualization module here. Okay, so result that directly leads to visualization module. So this is the undeformed shape of our model. It is undeformed shape. Okay, so in extracting result, let me say something. What we do, you will need to load output database by using file open, then navigate to the Abacus work directory, and then open the file called impsimulation.odb. This odb file is required. Let's go. What is that? So this is uh, the undeformed shape. So I'm going to when I click on this is the deformed status. Okay, and then counter plot. Yeah, deformed counter plot is this. This is a stress contour plot, and we can also visualize the displacement contour. This is the displacement. So these things, these texts are not readable, so we have to adjust these texts to visible. So for that, I'll go to B-port annotation option. On that, status block, then font should be some 14 or 12 or 14 like that. And another, the text type, I like Times New Roman text. Okay, somebody like any kind, but for me, I like Times New Roman font. So I select it and apply for all the, yeah, it is visible now. That's okay. And let me remove the boundary box. Yeah. So this is the visualization of stress. Okay. Different type of displacement. For example, U1. For example, U2. U3. Okay. U3. Again, for stress. For example, S stress one. Okay. Stress two direction. Stress in shear one two direction. Stress to three direction, and also other parameters that we define general contact domain. Anyways, mm, okay. So these all are there. And at the same time, we can simulate this work. Let me simulate it here. Animation scale factor, animation time history, animation harmonic, and animation options. Different things are there. Uh, People can use the here also. Here, many options are there. Okay, so let me animate it. This is the animation, impact animation. This is the impact animation. So it shows the response of plate as well as the impact. Okay. Another thing, we can go to the ODB file. So output database, we have impact simulation ODB file here. On ODB file, we have history outputs and other many parameters are here. So what are those history outputs? For example, we defined the displacement. So let me stop the animation and go to the ODB file. So for example, if I want to see the displacement time uh, of the impact system, this is a displacement time float of the impact system. Kinetic energy, okay, internal energy, artificial energy. Actually, this is very less, I think. Strain energy and different that force time float. Okay, contact area time float, contact area time float. So these all are there, and sometimes we can make we can extract the report file from here. Okay, so we can use some XY data. Okay, so these all are the steps which we use in this analysis. Okay, yeah. So what are those things? Let me explain it from the slide. Um, you can now explore the result of simulation because already what we have seen. From that, plot von Mises stress contour on the deformed mesh. You can now use the buttons to scroll through the history of the simulation. Uh, we can view animation of the impact by selecting animation time history. Again, one can like to see the plot counters of variables of von Mises stress. Okay, so many things are there. So one can read these slides and can understand. So another thing is advocacy allows us to post-process data. For example, if we want to save the contact force history to data set using tools, then XY data creates an ODB history from the XY data menu. So we can create this thing. What is this? Okay, tool XY data create the ODB history output, ODB field output. Yeah, so ODB history output, continue. Then all history output data are here. Okay, so we can create data of ODB data here, save as that XY data for report purpose. Okay. Again, ODB tools create XY data um, operate on xy. If I want to know, for example, here separately force time curve, displacement time curve, energy time curve only. It is a function of time only. But if I want to extract, or if I want to plot uh, the force time graph, that means force time graph, I will use operate on xy data and continue. I'll select the uh, that I mean force displacement. Okay, let me go to the combine. Here select. mm, yeah, combine x y data. First, the x-axis is displacement. So displacement u3, comma, and the y-axis is the force, total force, Fn3. So let me see the float expression. Yeah, you see here, this is force displacement, curve. Yeah, the force displacement curve in impact analysis shows that the amount of energy, the area under force displacement curve shows that the amount of energy dissipated during impact process. Okay, so this kind of combination also is possible. Okay, so uh, I'm saving this to my work directory on the, okay, that is abacus file from, not abacus file, but mm, yeah, anyway, we have to save this thing, and even at the very beginning we have to change directory of the work. So let me go to let me come out from visualization and then save the file, work directory. This work directory should be done at the very beginning, not later like this. Give some name of directory, uh, impact uh, simulation, impact simulation. Okay, what is that? Impact simulation. Sorry. Yeah, impact simulation. Okay, okay. I'm saving the file to this directory. Okay, where is impact simulation? We have, okay, impact simulation. This is hiding itself, sorry. Yeah, impact on impact simulation. Yeah, impact done. So this all what I have done is there on the this folder. We can see those things later. So yeah, okay. So So we have a lot of ideas on the slides. One can read these slides and uh, get important ideas. These are results which are extracted from the system. Okay, these are slides. These are okay extracted results. Okay, yeah. Thank you very much for your patience. This is when you are really happy with this. Uh, I promise you to continue with the laminated plates containing more than 4 or 8 laminates which stuck together. For that, I will also do for you. And for that, I need your response, whatever the response is, please. So thank you for very much.